So in the first part of this chapter series, I'd like to talk about how we encode a Taproot public key into a Bitcoin output. And this is done with SegWit version 1. SegWit version 1 encodes the Taproot public key. And in essence, it retains the same encoding format that we have from the previous SegWit version 1. We have a SegWit version byte, which has been bumped up to 1 now. And we have our program, we have our witness program, which in the case of SegWit version 1 is a 33-byte public key. Now the BIP Taproot or the BIP Schnorr continues to evolve, and it has in the meantime been updated to a 32-byte public key. But for the purposes of this workshop and the tools that we're using, we're going to continue to work with a 33-byte public key, but the idea remains the same. As we talked about before, a Taproot output has two different ways of spending. We have the default spending path, which is the key spend path, and we have the script path. In this chapter, I'd like to focus on the key path. Quick comparison between SegWit version 1 and the legacy pay-to-public key hash or pay-to-witness public key hash outputs. In version 1, we have the 33-byte public key in the output. This can be spent with a 64-byte Schnorr signature. Previously, we had a 20-byte public key hash, which is slightly smaller than the 33-byte public key. However, when spending, the witness requires, first of all, a dir signature, and in addition to that, the public key, since we're using a public key hash in the output. So as you can see, the witness is significantly heavier than the witness that we have in version 1, and therefore this implies a higher spending cost for version 0. The public key that we use in version 1 can be a single key or a musig. This is entirely indistinguishable on-chain. Taproot also retains the basic semantics of SegHash from previously. In general, the SegHash, all, none, single, and any, retain their meaning and their functionality. As you already know, SegHash is a way for us to determine or signal what part of the transaction we are signing. There is a new SegHash flag which has the same semantics as SegHash all. We signal that with a 0 byte, but it is implied because it is actually not encoded in the signature itself. And so to understand why that is the case, let's have a look at the way we encode Schnorr signatures in Taproot. Here we have a signature that's signed with the new implied SegHash all. We have the signature itself composed of the R and the S, 64 bytes, and we omit any SegHash byte at the end of the signature. This means that SegHash all is meant and implied. We are signing the entire transaction. If we want to use any of the SegHash flags, we need to append it to the back of the signature, therefore making it 65 bytes. We can reuse the same SegHash flags as before, all, none, single, and all. They retain their meanings.